Hello everybody, my name is Roman Fajardo and the title of my presentation is Combinatorics using Geometry. In combinatorics, there are a few processes we can use to select sets. Of course, the most well known is randomness. In my presentation, however, we're going to be taking a geometrical approach, where we want to figure out a way we can organize players into two teams in a fair way where each player gets to play the same amount of games with each of the other players, where x equals the amount of players and x minus 1 equals the amount of games. We're going to be taking an example where x equals 8 players and I have a research proposal where x equals 16 players. Some definitions before we get started. Galois field. Galois field is a basic field that contains a finite number of elements. During my presentation, we're going to be working with Galois field 2, which has an order pair of 0 and 1. We're also going to be working with hypercubes. Hypercube is a 4-dimensional cube. First, since we're going to be working with 8 players, we need to know that there's going to be 7 games between 2 teams, and each team is going to consist of 4 members. An approach to solve this problem is to view the 8 players in pairs instead of groups of 4. This makes it a bit easier to visualize. Next, we need to know that each pair of players has to be on the same team exactly 3 times. Next, we're going to assign each of the players to a vertex of a cube, as we see in figure 1 from 1 to 8. Knowing this, we're going to be working with Galois field 2 cube, which means we're going to be working in a 3-dimensional space, which also means that there's a linear equation that needs to be satisfied, which is ax plus by plus cc equals d, where a, b, c, and d are all real numbers except 0. The same equation can be applied to Galois field 2 cube, with the only difference being that a, b, c, and d are all elements of Galois field 2 cube, 0 or 1. Next step, we're going to break up the cube in 3 parallel ways, vertically, horizontally, and right down the middle, as we see in figure 2. This gives us 3 games. We can also use the equation 1x plus 0y plus 0z equals 1, giving us the outcome 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, which are precisely the red points on figure 2a. For figure 2b, we will be using the equation 0x plus 1y plus 0z equals 1, and for figure 2c, we're going to be using the equation 0x plus 0y plus 1z equals 1. Knowing this, the finite geometry of Galois field 2 to the cube has 14 planes that go through the point 0, 0, 0, meaning there are 14 ways of choosing A, B, C, and D. The equations that would correlate to this would be x equals 0, y equals 0, z equals 0, x plus y equals 0, x plus z equals 0, y plus z equals 0, and x plus y plus z equals 0. The other 7 planes would be the same, with the only difference being they are equal to 1 instead of equaling to 0. In order to get the last 4 figures, we will use the following expressions: x plus y, x plus z, y plus z, and x plus y plus z. And if the equations equal 0, the points are red. If they equal 1, the points are green, as we see in figure 3. And here are our results. The following table is from our previous 2 figures, figure 2 and figure 3. As we can see, each pair of players is on the same team 3 times. For example, if we were to take pair 1 and 2, we can see they're on the same red team 3 times, in game 1, game 2, and game 4. Alright, now for my research proposal. We were to take the same approach, but this time instead of working with 8 players, we're going to be working with 16 players. Likewise, with the first example, we would be working with Galois field. However, we're going to be working Galois field 2 to the 4th power instead of Galois field 2 cube. This means we're going to be working in a 4-dimensional space, which also means we're going to be a linear equation needs to be satisfied, which is ax plus by plus cc plus dw equals z, where a, b, c, d, and e are all real numbers except 0. This same equation can be applied to Galois field 2 to the 4th power, but with elements of Galois field 2 which are 0 and 1. Next, we're going to appoint each of the players to a vertex of a hypercube as we see in figure 4 from 1 through 16. Likewise, in the first example, we're going to break up the hypercube in 4 parallel ways. We can break it up in a horizontal way as we see in figure 5a, in a vertical way as we see in figure 5b, and in 2 diagonal ways as we see in figure 5c and d. Next, knowing this, we know in Galois field 2 to the 4th, it has 30 planes that go through the point 0, 0, 0, meaning that there are 30 ways of choosing A, B, C, D, and E. The equations that would correlate to this would be x equals 0, y equals 0, z equals 0, w equals 0, and so on. The other 15 equations would be the same, but instead of equaling 0, they're going to equal 1, with x equals 1, y equals 1, z equals 1, w equals 1, and so on. Now, to get the last 11 figures, we're going to use the following expressions, where x equals x plus y, x plus z, x plus w, and so on. In conclusion, and some further research. In conclusion, this process has not been proven, but it's yet to believe to work with numbers that are divisible by 4. Except 12. 12 is a special case. It is believed that it's only worked for 16 and above. Some applications to this could be sporting events. For example, track and field. If we have a select number of events and a select number of players, we can use the same process, just different numbers with the same process. Alright, here are my references. And any questions, feel free to email me. Thank you. Bye-bye.